3, 2, 1. Howdy, howdy, this is Mr. Potter. In our last video, we talked a lot about the difference between functions and relations, and in this video, we're going to be talking about one-to-one functions as well as parent functions. And so I first want to talk about what do we mean when we're talking about one-to-one functions. So a function is one-to-one if each element in the range corresponds to exactly one element in the domain. And so I want to talk about what I mean by that. Remember that we did have some functions where I could have a number in my domain map over here to a number in my range. I could have another number map to that same, and then a different number map to a different. The idea is that this is okay for a function. It's okay for me to have multiple values here mapping over to one value in my range, but it's not going to be a one-to-one function. In other words, it's not going to allow me to go backwards. If I know that my function returns a 4, it's hard for me to say what is x. Is it 1? Is it 2? Is it some other value in my domain? And that's the problem. Essentially what I need is if I have numbers over here in my domain, in my range, any number over here should correspond to exactly one number over here. In other words, I shouldn't have overlap. Now, obviously, if numbers over here were to map to multiple numbers over here, say if this was also to map to a 6, then this would not be a function because one element in my domain maps to multiple elements in my range. If, however, every element in my domain mapped to a different element in my range, then this actually gives me a one-to-one function. So I want to talk a little bit about some examples of functions that are one-to-one and some that aren't one-to-one. And so I've got two examples here. One is y equals x squared. And we're familiar with this. This is our typical parabola that we originally learned in Algebra 1. We worked with a lot in Algebra 2. And over here I have the geometric formula, area equals pi times r squared. This is the area of a circle. And the question is, what does one-to-one mean? Well, if I'm looking at y equals x squared, I can think of a domain and range. If I were to take values like -2, -1, 0, 1, and 2, these are going to map to 4, 1, 0, 1, and 4. Notice that 1 and -1 both map to the same y value in my range. Similarly, 2 and -2 map to the same y value. So this is not one-to-one. Keep in mind, though, when I'm talking about the area of a circle, -2 and -1 have no real meaning over here. There is no way to have a negative radius give you any type of area. A circle with a radius of 0 would map to 0. A circle with a radius of 1 would map to 1, a circle, or pi, I should say. A circle with a radius of 2 would map to 4 pi. And in this situation, every value in my range has a corresponding radii that gave it that value. Even if I have a number like 17 pi, there is some value over here in my x, notably the square root of 17, is the one value in my domain that would have given me that. So this is an example of a function that is one-to-one because of the domain restriction that x has to be strictly greater than or equal to 0. That comes from the nature of geometry, though. So I could have functions that are very similar, but because of a domain restriction or because of some other quality, I'm going to end up with a one-to-one situation or not a one-to-one situation. So let's talk about the vertical line test. Oftentimes when I'm thinking of a function, let's say I'm dealing with a function like y equals x cubed. If I look at a function like y equals x cubed on a graph, I know that it's got this type of shape to it. And we're going to be talking about all of these different functions that we've talked about in our previous math classes. Anytime that I draw a vertical line, the vertical line is going to intersect my graph at most one x value. And that one x value is going to correspond to one unique y value. In other words, every y value is going to have some point that corresponds to a unique x value. And so if a function passes the vertical line test, then it is one-to-one. Even if I'm dealing with a more complicated cubic function, say one that goes up and then down and then back up again, which we've seen cubic functions like this before. No matter where I draw my vertical line, a vertical line is going to intersect this graph at most one point. And if every possible vertical line does that, then that means that these functions are going to be one-to-one. If I were to take, say, an ellipse, which is a shape that we talk about in Algebra 2, I know that if I have an ellipse, of course, this isn't even a function, but just because I draw that vertical line, any vertical line is going to intersect at more than one spot. This is not one-to-one. Well, what if I deal with something like x equals y squared? This is going to be a graph that looks like this, where the x value is going to be whatever the square of y is. And if I draw a vertical line, then I'm going to intersect that graph at more than one. So these are examples of what not one-to-one is. And the key for this is understanding this vertical line test. If I can draw a vertical line, every vertical line is going to intersect the graph at most one point, then we're dealing with a function that is one-to-one. Now, we'll often talk about something called the horizontal line test. So in other words, similarly, we can use a horizontal line to test if a relation is one-to-one. So in other words, if every horizontal line would intersect a graph more than once, then the graph does not represent a one-to-one relation. So I could look at something like this graph here, and we'll talk about what this function is later on in this course, but something like this, no matter how I draw my horizontal lines, notice that my horizontal lines are always going to intersect that graph at most one point. If I were to look at a function like this, and again, notice I'm not talking about functions, I'm actually talking about relations. If I were to look at the horizontal lines here, these actually do pass the horizontal line test, even if it doesn't pass the vertical line test. So I can use the horizontal line test to talk about the relations being one-to-one. So what I want to talk about next is I want to talk about some parent functions. Now, when I'm talking about parent functions, I'm talking about functions whose graph represents fundamental behaviors. In other words, when I talk about a parent function, I'm actually talking about graphs that they represent some fundamental behavior that all graphs of that particular form do. And of course, the only differences that we're going to see is we're going to see some transformations. In other words, we'll see some translations. We might see some dilations where something is stretched vertically or stretched horizontally, or just simply moved up or down. So that's what we're talking about when we're looking at parent functions. Now, almost every more complicated function can be represented by a parent function that has very simple behaviors to understand. So what we'll often talk about is when I'm given a more complicated function, what is the parent function? That's going to help us understand the underlying behavior that we're trying to understand. So let's talk about the constant parent function. Now our constant parent function is going to be a very simple function, just y equals 1. In other words, given coordinate axes, x and y axes, my parent function is just going to be a constant function. In other words, my y value is going to be consistently just 1. Now notice I can translate this graph up or down to represent any constant function, any function where the y value stays the same. But to understand the basic behavior, I'm basically looking at what happens when y is 1. So in other words, for x value, I could look at -2 or -1 or 0 or 1 or 2, but y is always going to be 1. Now, a linear function is slightly different. A linear function is, of course, going to be a straight line, but it's not necessarily going to be a horizontal line. And so our parent function for the linear function is y equals x. Now, y equals x has some basic behavior, but I can take this function and I can do two things with it. Number one, I can translate this up or down. Translating it up or down changes where it intersects the y-axis, changes its y-intercept. And I can also change the angle, basically stretching it vertically or stretching it horizontally, and that's going to change the slope. So any function that I could think of the form m times x plus b, where m and b are constants, I can think of as a parent function y equals x, kind of having the basic behavior that I'm looking for. And so from a table, I'm looking at something that's going to have a constant rate of change. So -2, -1, 0, 1, 2. Y is going to be whatever x is. And one of the basic ideas that we notice about linear functions is that we have a constant rate of change. This is always going to go up by the same amount. In this case, it's going up by 1. That rate of change is called the slope. Now, again, these should be very familiar, but I want you to think of all the different ways that we could transform these functions. And if I had a transformation of functions, could I recognize the parent function? So higher degrees, we have quadratic and cubic. So quadratic formula, a quadratic function would have its parent function be y equals x squared. And we're familiar with the shape of a quadratic function. Basically, it's a parabola. So we're familiar with this U-shaped graph. And I'm also familiar with the notion that no matter what my x values are, a -2 or a +2 are going to have the same y values. -1 and +1 are going to have the same y values. And we talked about this being an even function. Even function because the values on the right side of my y-axis are the same as the values on my negative part of my x-axis. In other words, f of x is going to be equal to f of -x. This is a property of even functions. And this behavior, this type of curve, I can imagine stretching it. I could translate it horizontally. I could translate it vertically. And that's going to be any function that's going to be of this form ax squared plus bx plus c. I can think of that as a transformation of my parent function, y equals x squared. Similarly, I can talk about the cubic just being y equals x cubed. And the cubic function has a typical graph as well. Usually, it has one part that goes upwards arcing, and the negative values are going to go downwards arcing. And so this idea here that f of negative x is equal to negative f of x is what we think of as an odd function behavior. Odd because we're dealing with an odd exponent. This is almost the same as what we saw earlier with our x to the first, or our linear function. And anytime that I'm dealing with an even exponent or an odd exponent, I'm going to see this general notion of shape. The shape may be narrower or wider, depending, but in general, I'm going to see this kind of feature when I'm dealing with even functions or odd functions. And we'll talk more about that later. But I can think of my table over here for x and for y, and if negative 2 cubed is a negative 8, then positive 2 cubed should give me a positive 8. In other words, changing the sign of my domain should also change the sign of my range. Negative 1 gives me a negative 1, positive 1 gives me a positive 1. And of course, we're going through the origin, going through 0. Now, this is the parent function for any cubic, which I can think of as ax cubed plus bx squared plus cx plus d. And that's going to handle any situation, any type of horizontal or vertical shift or translation, any vertical or horizontal dilation or stretching. So that takes care of our polynomial situations. We do have other parent functions we're going to be talking about. So I've got absolute value and exponential. The absolute value function I can think of as y equals the absolute value of x. In other words, what happens when I take this sign away? In other words, it's equal to whatever x is if x is greater than or equal to 0, and it's equal to the opposite of x if x is less than 0. And this idea of breaking up a function into two pieces is something else we'll talk about later. In general, the graph is going to look a lot like a V. Now, it's always going to be positive, but the pieces are going to be linear. And notice that what happens here is this point over here for this value of x matches the y value for this negative x. So this is an example of an even function that has linear pieces. So if I were to look at this from a tabular standpoint, I've got x and y. Negative 2 is just 2. Negative 1 is just 1. In other words, if it's negative, I just take the sign away. The opposite of a negative 2 is positive 2. The opposite of a negative 1 is positive 1. 0, of course, is 0. 1 is 1. 2 is 2. If x is already positive, then I just take a look at what x is. So this is one example. I can also talk about exponential functions. In other words, where y equals something, let's call it 2 to the x. Now, I'm using 2 as the base of my exponential parent function. Later on, we're going to find a better number to use for that. But the idea is just to get the idea of a curve. And when I'm looking at this curve, I know that 2 to the 0th power is 1. 2 to the first power is 2. 2 to the second power is 4. And this thing's going to shoot up. But if I take a look at negative exponents, I know 2 to the negative 1 power is 1/2. 2 to the negative 2 power is 1/4. And so this is going to get closer and closer and closer to 0 without ever actually touching it. Now again, this is my parent function, so any other exponential function I can think of is just being some transformation of this function. Negative 2 gives me 1/4, negative 1 gives me 1/2, 0 gives me 1, because anything to the 0 power other than 0 is 1. 1 gives me 2, 2 gives me 4, and this is going to shoot up very high. So we have the absolute value and the exponential function. Some other parent functions we have, the reciprocal and the reciprocal squared. If I have y equals 1 over x, this has some very special behavior. First thing that I need to know is that if x is 0, then this is undefined. In other words, this is the first graph that actually has a gap in it. Every other graph that we've talked about so far has been pretty much a continuous straight through. But for us, the reciprocal of 1 is 1. The reciprocal of negative 1, is negative 1. The reciprocal of negative 2 is negative 1/2. The reciprocal of positive 1 is 1. The reciprocal of 2 is 1/2. So what I'm going to notice is 1 gives me 1, 2 gives me 1/2, 3 is going to give me 1/3. This is going to get closer and closer to the x-axis. Both sides, excuse me, that's wrong. Let me fix that. Both sides are going to be closer and closer to the x-axis. This is going to be approaching from the bottom. This is going to be approaching from the top. As I get closer and closer, I can say, okay, well, what happens if x is 1/2? Well, the reciprocal of 1/2 is 2. The reciprocal of 1/3 is 3. In other words, as I get closer and closer to the y-axis, this is going to increase. And similarly, for those negative values, this is going to decrease, getting a -2 and a -3. And so this is our first graph that actually has what we call an asymptote. And we'll talk a little bit more about what we mean by asymptotes in a later video. Now for the reciprocal squared function, the main difference here is that I've got y equals 1 over x squared. So these graphs are actually going to get closer to their respective axes much quicker. -2 squared would give me 4, and so that's going to be 1/4. -1 squared is 1, so that's going to give me 1 over 1, or 1. 0 again is still undefined. Positive 1 is going to give me 1. Positive 2 is going to give me 1/4. So again, I'm going to see very similar behavior to this curve. 1 is going to give me 1, 2 is going to give me 1/4, 3 is going to give me 1/9. It's going to get closer and closer. But on the negative side, these values are positive because the exponent is positive. This is another example of an even function. And of course, as I get closer to the y-axis in positive and negative, again, I'm going to have that asymptote situation. So we have the notion of a reciprocal and a reciprocal squared function. The last two parent functions we're going to be talking about are the square root and the cube root function. So if I deal with y equals the square root of x, and again, I can transform this by moving this up and down, left and right with constants on the inside or constants on the outside, either being multiplied or added. But the idea here is that the square root of numbers is going to give us some particular behavior. First off, I can't take a number like -2 or -1 and take the square root of it. That's going to cause some problems. These are undefined. The square root of 0 is 0. The square root of 1 is 1. The square root of 2, well, that would give me the square root of 2, about 1.414. The square root of 3 is about 1.732, again, approximately equal. The square root of 4 is 2. And so what I'm going to notice is, if I look at this graph, first, I'm not going to have anything over here. It's actually going to start at the origin and start, but it's going to slowly arc this way. As x increases, the amount of change in y is going to be very small. So I've got y equals x squared, and of course I've got this restriction on my domain that x has to be greater than or equal to 0. Similar to how we had a restriction in our domain for our reciprocal functions. If I take a look at the cubed root function, something like y equals the cubed root of x, two things happen. Number one, negative numbers are perfectly acceptable. So I can have -1, and the cubed root of -1 is -1, because -1 times -1 times -1, or -1 to the third power gives me -1. If I take the cubed root of -8, that's going to give me a -2, because -2 times -2, which is 4, times another -2 gives me -8. 0 gives me 0, 1 gives me 1, 8 gives me another 2. So I'm not going to have the restriction on my domain that the square root function had. What I'm going to notice is that this is going to increase much slower, but it's also going to have this behavior over here. So it's going to look an awful lot like a cubic function, just rotated or reflected. And again, I can translate this up or down. I can translate it side to side. I can stretch it vertically or stretch it horizontally just by changing coefficients here, adding amounts inside the radical. I can also add amounts outside the radical. I can have a coefficient outside of the radical. These coefficients, these added numbers that I'm either multiplying or added, are going to change the appearance of my graph, but they're not going to change the behavior of my graph. Parent functions help give us the behavior that we expect. Everything else is just a geometric transformation. Once again, this is Mr. Potter. Thank you for watching. Have a great day.